Welcome to this MedEWSa e-learning slide deck about compound events in multi-hazard risk analysis. We will introduce compound events, their types, and the methods often used to detect and evaluate them. We will also highlight why they are important when analyzing multiple hazards related to meteorological and hydrological events. Statistically speaking, compound events involve two or more events happening together. It can be independent events, in which the outcome of one event has no effect on the probability of the other, or dependent events, when the outcome of one event affects the probability of another. Compound events can thus be decomposed into two or more sub-events, and can represent a combination of multiple outcomes. Rolling two dice, for instance, is an example of a compound event. Given that the two dice are rolled at the same time, we could be interested in knowing, for instance, the probability of getting a sum of 11, as shown in the figure. Compound weather, climate, or hydrological events refer to combinations of multiple drivers or hazards that lead to potentially large impacts. Events can be related to extreme conditions, such as storms, heat waves, floods, and droughts, or to combinations of events that are not themselves extremes but lead to an extreme event or significant impact when combined. The focus on impacts brings stakeholders to the heart of the process, as they play a key role in identifying the impacts and the interactions among hazards that lead to a particular outcome. A widely adopted classification of compound events identifies four main types of compound events: preconditioned, multivariate, temporally compound, and spatially compound events. Preconditioned compound events occur when one or more hazards cause or amplify the impacts of a pre-existing climate-driven condition. A typical example is the case when heavy precipitation falls on already saturated soils. This type of compound event is closely connected to cascading events, when a primary hazard triggers a sequence of hazards. In multivariate events, multiple simultaneous climatic impact drivers or hazards occur in the same geographical region. For instance, this is the case of compound flooding, which results from multiple flood drivers such as precipitation, river discharge, and storm surge, and poses a significant risk to coastal communities. The category of temporally compound events refer to successive hazards that affect a given geographical region, leading to or amplifying an impact when compared to a single hazard. This is, for instance, the case of successive storms affecting the same area and amplifying riverine floods. Spatially compound events occur when hazards in multiple connected locations cause an aggregated impact. The 2022 compound drought and heatwave, for instance, caused widespread crop damage, water shortages, and wildfires across Europe. A wide range of approaches and tools have been applied to investigate the strength of the relationship between multiple climatic impact drivers and to assess multi-hazard combinations. These combinations result in a complex system, and their physical understanding, representation, and analysis often require approaches adapted to the type of compound events we may be interested in and the datasets available for their analysis. Statistical methods, including regression, multivariate statistics, and classification, are largely dominant for detecting, predicting, and understanding relationships among different datasets. Empirical representations are observation-oriented and aim to detect correlation between variables based on large amounts of historic data available. In the case of complex dependencies and high-dimension applications, the use of statistical tools such as copulars can be beneficial. This is in particular the case when the number of features to be analyzed is very large. Network-based techniques help identifying non-trivial spatiotemporal patterns of extreme events, which can be suitable to study compound extreme events at different geographical locations. Finally, the use of physically based models, such as global and regional climate models or hydrological models, contributes to the identification of cascading and triggering conditions in compound events. The study of multi-hazard interactions can serve different purposes. It enhances our knowledge and understanding of the drivers that affect the risk of compound events at local or large scales to society and the economic sectors that depend on climate, weather, and water, such as agriculture, renewable energy, flood protection, health, and environmental preservation. For instance, in 2022, Pakistan faced a record-breaking heatwave that was followed by unprecedented monsoon rains, resulting in flooding that caused 1,486 fatalities and approximately $30 billion in economic damages. The detection and characterization of compound events can also inform forecasters and emergency responders of the potential aggravation of impacts due to unusual co-occurrences of extremes forecasted by early warning systems, such as simultaneous or sequential hazardous events. A recent study in Denmark, for instance, has shown that the lack of a framework to handle overlapping hazards across both temporal and spatial scales can impact resource allocation and response prioritization, as municipalities are required to manage simultaneous risks at different locations. Compound event analyses can also support stakeholders and policymakers in addressing future risks from an increased frequency of these events and their impacts that can have a cascading effect on strategic adaptation and planning. For instance, studies have indicated that regionally extreme hot and dry conditions, such as the summer of 2018 in Europe, are expected to become more frequent in the future. In summary, we can say that high-impact compound events come in many different forms and reflect combinations in space and time. The combination of multiple drivers and/or hazards can create amplified societal and environmental impacts. Understanding the typology of compound events can help their analysis by facilitating the selection of appropriate datasets, methods, and modeling tools. Multi-hazard analyses can be useful to enhance our understanding of past compound hydrometeorological events, but also to prepare our societies to future risks in a changing climate and a changing world.